Basicity of organic compounds. We'll first compare the basicities among amines, phenylamines, and ammonia. Thereafter, we will expand beyond that. Let's start off with amines. Amines like ammonia are proton acceptor because the nitrogen is highly electronegative and they actually has a lone pair electron. So the strength of a base depends on the availability of the lone pair electron to act as a proton donor. So there are two factors that will affect this availability. The first factor is the presence of electron releasing group. The more electron releasing group that nitrogen is bonded to, then the more available lone pair electron will be to act as proton donor. The second is to examine the various groups that are bonded to nitrogen, whether they crowd around the nitrogen and sterically hindered the nitrogen atom from using its lone pair electron to form coordinate bonds with protons. So firstly, we can establish the relationship that all amines will be a stronger base than ammonia, primarily because they actually are bonded to at least one electron releasing alkyl group. And we will expect secondary amine to be a stronger base than primary amine because there will be two electron releasing alkyl groups bonded to the nitrogen in secondary amine. And we can also conclude that tertiary amine will be the weakest base among all the amines, primarily because the lone pair electron of nitrogen now is sterically hindered by the presence of the 3 alkyl group to act as a proton acceptor, therefore reducing its ability to accept H+. Finally, ammonia will be a stronger base than aromatic amine, primarily because in the case of phenylamine, the lone pair electron of nitrogen will overlap with the delocalized pi electrons in the benzene, rendering it less available for coordination to a proton. Thus, in conclusion, we can safely say that amines are stronger bases than ammonia, ammonia stronger than your phenylamine. Let's continue now on the strength of the various phenylamine, where a different Y group is bonded to phenylamine. Let's consider now your methyl group, which is a ring activator. If it ring activates the benzene, it means that the overlap between the lone pair electron of nitrogen and the delocalized pi electron becomes less extensive. Therefore, the lone pair electron of nitrogen is now more available for proton coordination. Therefore, we expect methyl phenylamine to be a stronger base than phenylamine. Let's now take a look at another Y group. For example, NO2 group, which is here. So NO2 group is a ring deactivator, and if it deactivates the benzene, then the overlap between the lone pair electrons of nitrogen and the delocalized pi electron will be more extensive, and end up the lone pair electron of nitrogen is less available for proton coordination. So in that case, the compound will be a weaker base than your phenylamine. Let's take a look at why amine is a stronger base than your imine. So what is imine? Imine is a compound with a functional group C double bond N. So in this case, we need to note that the nitrogen is actually sp2 hybridized. While in the case of your ammonia or your amine, the nitrogen hybridization is sp3. We need to note, and it's important to note that amine with a sp2 hybridized nitrogen, which specifically means imine, are less basic than sp3 hybridized nitrogen. The reason is because sp2 nitrogen has greater S character and more tightly bound to nitrogen, leading to greater steric hindrance and lower spatial availability of the nitrogen atom to interact with protons without hindrance. So hence, imine is a weaker base than your ammonia or your amine. A good example to look at, if you were to compare this nitrogen and this nitrogen here, we can safely say that this nitrogen is a stronger base, primarily because it's a sp3 nitrogen, while this nitrogen here is sp2. With that, we can say that amine is a stronger base than ammonia, ammonia is stronger base than your imine or your pyridine. And remember, your pyridine's nitrogen is also sp2 hybridized. And let's now take a look as to why pyridine is a stronger base than your phenylamine and your pyrrole. This is structure of pyridine, this is structure of phenylamine, and this is structure of your pyrrole. In the case of pyridine, nitrogen is sp2 hybridized, this nitrogen is sp3, and the nitrogen here is also sp3. Then why is it not the case that the sp3 nitrogen is a stronger base as it has less S character? The reason is because in the case of phenylamine and your pyro, in the case of both, they overlaps with the pi electrons. So for phenylamine, it delocalizes with the pi electrons in the benzene, while in the case of pyro, it actually overlaps with the pi electrons, the two C to C double bond, which are of close proximity to nitrogen. Hence, because of that, it will render both its lone pair electron less available for proton coordination. So in summary, amine is stronger than ammonia because it has more electron releasing group that bonds to nitrogen, rendering the lone pair electron to be more available for proton coordination. And also to add that tertiary amine is the weakest base amongst all the amine, primarily because it has 3 alkyl groups that's bonded to nitrogen, historically hindered the lone pair electron of nitrogen for proton coordination. Next, in terms of nitrogen, which is sp3, relative to sp2, like in the case of pyridine and your imine, which is a C double bond N, and sp2 nitrogen would have more S character, and therefore because of this, its lone pair electron will be more sterically hindered for proton coordination. Hence, imine and pyridine are weaker base than ammonia. Relative imine and pyridine to phenylamine and your pyro, you will find that they are a stronger base. The reason for that is because in the case of phenylamine, the lone pair electron of nitrogen overlap with the delocalized pi electrons, rendering it less available for proton coordination. Similarly, in the case of pyro, you will find that the lone pair electron of your nitrogen will actually overlap with the delocalized pi electrons. There's 2 C to C double bond here. So the pi electrons from the C to C double bond will overlap with the lone pair electron of nitrogen, rendering the lone pair electron of nitrogen less available for proton coordination. And in the case of pyridine, despite the fact that the nitrogen is sp2, the lone pair electron does not overlap with the delocalized pi electron in the benzene ring. Hence, pyridine becomes a stronger base than your pyro or phenylamine. Finally, amide is neutral, so hence it is the weakest base.